Right up there. Sweet. My name is Nicole Aiken. I am a fourth-year PhD student working in the Conduit Structural Petrology of the Lithosphere Lab, and I am, once again, the chair of this year's ESS Gala. Thank you, Jody. I just want to thank everyone in the community for showing up for the first 3 days of this research symposium. We've had some incredible talks ranging from geohazards and society, all the way over to our Earth and planetary sciences and geobiology, as well as glaciology and all of the other fantastic talks. So thank you to all of our participants, thank you to all of our judges, thank you to all of our audience members. Can we have a round of applause for everybody in the community who makes the Gala what it is? Excellent. This year we have 60 photo contest entries, so please make sure that you are looking at those on the website and voting, because that will close tomorrow at noon. And I'm also happy to say that as of earlier this afternoon, we have raised over $5,000 for the department. I am optimistic that by tomorrow we can at least match last year's of $6,000. So if you are willing to help us get there, please feel free to share that link with your friends, families, networks, and otherwise, we hope that you are enjoying the gala. And without further ado, I'm going to invite Jody up here to introduce our keynote speaker.
Thanks, Nicole. Well, I'm Jody Bourgeois. I'm Professor Emerita, and I'm a sedimentary geologist. So why am I introducing a space physicist? Well, for one thing, sadly, we lost Robert Wingley back in 2021, who was Carol's advisor, and he would have been thrilled to have introduced you today. Noelle was reminding me that that Carol and her partner, Joe Dufek, were here as a power couple early in their careers and gave the speech at our graduation ceremony. That's like, Noelle, remember? That's like so far back you don't remember it. Right. So, but I've known Carol since she was a grad student here. And maybe I'm introducing her because she kindly put up with my really stupid questions that I would ask at talks she would give. But I likened her planetary magnetosphere diagrams to Linus's hairdo. So,
Something I will never forget.
Right. So Carol is a planetary and space physicist, specializing in ice giant magnetospheres, moon-magnetosphere interactions, and icy moon interiors, with simulations and spacecraft observations and modeling. And she's co-investigator on Clipper, which we'll hear more today about the specific things she's doing. She's on a team that's planning outer planet explorations out to Uranus and Neptune, for example. That's amongst her recent things. And she recently served on a National Academy panel for the Planetary Science and Astrobiology Decadal survey. Carol got her degree here in 2006. She worked on the magnetosphere of Ganymede. Is that correct?
That's right.
I couldn't say that much. And then she did postdoc, and after that was on the faculty at University of Georgia. No, Georgia Tech. Uh-oh, be careful. I know we have Georgia Tech. And then came to University of Oregon 10 years ago.
7 years ago.
7 years ago?
Yeah.
She was the director for a while of the honors program of the whole college, right, at University of Oregon. And one other thing I remember about the time Carol was here, she was actually part of a group of what I call the space women. So there are actually 5 or 6 women that within Robert Wingley's group over a period of years that overlapped that got degrees in space physics. Of course, she started at Bryn Mawr, which is also one of the birthplaces of women in geology. I was reminding her, so she has a long history of being a power woman in science, I'll say. So I'm pleased to have her here, and I hope you'll enjoy her talk. Thank you.
Thank you. you so much, Jody, and thank you all for inviting me out here to talk to you. It always feels a bit like coming home, coming back to Seattle and to University of Washington. Although, my gosh, it looks so different. Campus looks different. I don't even understand what road I'm on when we're driving in because there are so many more buildings and things like that. Oh yeah, if there's a way to dim the lights, the slides will look way prettier, but I have no idea how to do that. Oh, I think Anton has worked it out for us. Perfect. Oh, wow. I mean, that's okay, because then you don't get to watch me do crazy things with my hands. I'll let you work on that while I do. I wanted to, before I get started on a journey to Jupiter's ocean moon, Europa, I thought I would just tell you a little bit about my journey and how really fortunate I feel to be here. And yes. Oh, okay. I trust you. How fortunate I feel to be here because, there are so many stages in one's academic journey and one's professional journey where things could turn in a myriad of different ways. And so I was reflecting on that as I was putting this talk together, thinking about a journey to Jupiter's ocean moon. And I thought, I'll say just a few words about my journey and how I ended up where I am now. It feels like a lifetime ago, or maybe yesterday, that I was in Johnson Hall working on my PhD. It's hard to say which because it's confusing when you get old and your brain gets mushy, and it feels like this is home, and yet I haven't been here for 20 years, and so that's a crazy feeling, other than to visit. But I guess before I got to the University of Washington, I told my parents, okay, I'm finishing undergrad at Bryn Mawr and I'm going to go to Seattle. And they're like, you know where? I'm from New York, up in the Catskills, and my friends and family thought Seattle was like a foreign country, which, I mean, if you're from New York, I don't know if anyone is, you know that the world is New York and everything else is far away, because New York is the center of the universe. And so they thought Seattle was like the most bizarre, odd choice ever. But while it seemed unlikely, it was really a bunch of fortunate events that pushed me here, right? And those fortunate events were people. They were colleagues, they were professors, they were friends in my undergraduate realm that pushed me in this direction. I had fellow students who convinced me that I should study abroad, that it would be really good for me to do. And it was at St. Andrews that I took my first magnetohydrodynamics class. And I thought, oh, I love this area of physics, magnetohydrodynamics. What a great thing. And then I came back from study abroad, and I had the good fortune to do a summer internship at NASA Ames in the Astrobiology Academy. And David Catling happened to be my undergraduate summer mentor there, among others. But he was very instrumental in my understanding that planetary science was really a thing, not just a fantasy, not just Star Trek for grown-ups. But so I had the good fortune of meeting David there as a mentor. And then I also had the good fortune going back to Bryn Mawr to take my first applied physics class in geophysics with Juliet Kreider while she was a professor at Bryn Mawr. And she said, you know what you should be looking at for graduate school is University of Washington. I didn't know that they were about to move out to Seattle as well, but she said, you should look in that program. I think based on what you're saying, you're going to really like geophysics and space physics out there, and take a look. And of course I did. I came to visit, and I met Robert Wingley, among others, on the space physics program, and I thought, wow, this is where I'm supposed to be. It was very clear to me right out. I don't even know that Robert knew I was supposed to work with him, but I knew I was supposed to work with him. And that made all the difference in terms of where I landed, getting here. He gave me ultimate freedom to choose my project. And so as Jody said, I ended up modeling Ganymede's magnetospheric interaction with Jupiter's large-scale magnetosphere, which sounds like a crazy project. And Robert had never done a planetary PhD student before. He was only doing Earth, but he had this fantastic model that he had just developed, this multi-fluid magnetohydrodynamic model, and it was the right tool, the right novel tool to hit this incredible data set at Ganymede that had just come down from Galileo and Hubble Space Telescope. We had plasma instrument data, we had magnetometer data, we had plasma wave data, and we had UV aurora from Hubble Space Telescope, and trying to develop this framework with a model to integrate all these disparate observations and create a holistic picture of what was going on turned out to be the best thing I could have ever done for a PhD project, because it set the stage for me to move on to my postdoc working on Cassini data at Enceladus and Saturn. Moving on to Georgia Tech, I realized that what I really loved was comparative planetology, or really comparative planetology magnetospheres edition, right? Because I don't, as you will see from this talk, I am not a geologist, as much as I pretend to be one sometimes in class. But I love the idea of using the physical framework, using physics as a governing model for understanding how these really different planets, which really are just expressions of different boundary conditions, how they work. And that's really, again, I haven't really specialized so much on any one planet, because I've moved from Ganymede to Enceladus, Saturn's magnetosphere, which is huge compared to Ganymede's, and then Mars' atmospheric electrodynamics, Mercury, and then back out to the ice giants. So I've really hopped around, but with the same principal mode in mind, which is trying to apply modeling to integrate diverse data sets to try and paint a holistic picture of what's going on, what boundary conditions are driving the expression that we see in the observations. Okay, so that was my journey and how I ended up, roughly speaking, where I'm at right now. And what I'm going to talk to you today is the journey to Europa. And this has been a long journey, as you'll get a chance to hear during the talk. And I won't even go into the early history, like the GMO days and the EJSM days before Clipper was born out of the ashes of EGSM getting burned down in the prior decadal survey. But that's where we're going to begin, is with Europa Clipper. But actually, we're going to begin even earlier. So obviously, beginning with Galileo Galilei back in 1610, using the telescope, he was the one who really discovered the Jovian system of worlds, and that inspiration has provided a just incredibly rich paradigm change back then, because you had worlds orbiting around a more different world, to now, where the paradigm shift is really been one of changing our understanding of the Goldilocks zone, or what a habitable environment or a habitable region around a star looks like. No longer are we resigned to this little band, right? A little band where liquid water can exist at the surface of a world because of solar radiation flux. But we're thinking about subsurface oceans far out in the solar system, driven by tidal forces that create a habitable environment to explore. So really, Europa has been a paradigm changer back in the 1600s and through today. And just, oh, see, I knew I would do that. Just because, nope. There we go. Just to, I don't know if we can make it any darker, but just to remind us of what we're looking at here, what Galileo saw was Jupiter, which was a finite spot in the sky, not a twinkling star, through his telescope. And he saw 4 points of light that were orbiting around it, periodically, predictably. And they wink out in the back when they go through kind of the solar shadow that Jupiter provides. But this is what he documented. This is what he presented to the world back in 1610. And of course, from there, we move on to thinking about the observations that Galileo, the spacecraft, not the human looking through the telescope, brought us hundreds and hundreds of years later. So the Galileo spacecraft, which is highlighted, try not to advance the slide, down there, orbited Jupiter from 1995 to 2003, when it took a nosedive into Jupiter on its last orbit. And from that mission, which was roughly 34 orbits around Jupiter, and actually I've got a little inset here to show you. This is what we call a petal plot, but this is what the orbital path of Galileo looked like, orbiting around Jupiter, and on each of those orbits, also flying by one of these 4 moons on its path. And so actually the names of the orbits of Galileo are based on which moon it passed. So we have the E4 orbit, which was the 4th orbit when it passed by E for Europa, or the G8, which was the 8th orbit, G for flying by Ganymede in that orbit. And from this 34 orbit mission, we learned so much more about Io, Europa, Ganymede, and Callisto than we did from Galileo. We knew so much more about them, and they provided this diverse spectrum of icy worlds in the Jovian system for us to go back and explore. And the one, okay, and here I'm of divided loyalties. As I said, I started on Ganymede, which is my favorite moon in my heart, but Europa was a pretty darn exciting moon as well. It didn't have its own magnetosphere, but gosh, when we looked at the surface of Europa, it just presented us with a compelling story and so many more questions than answers, right? I'm going to just highlight a couple of these different surface features that were observed. Some of them are in enhanced color scale so that you can see them a bit better. But basically, we had things like ridged planes where you see this looks almost like the surface has just been a wound up ball of yarn, fractures that you can trace along the surface, fractures overlaying fractures, overlaying fractures, overlaying fractures, telling us about the very dynamic history, tectonic history at the surface of Europa. And these are, again, I have some scale bars on here to give a sense of size and scale of what's going on at the surface here. There were also these incredible banded features that, again, in false stretched color, you can see compositionally look different than the surrounding, almost as if material came up and melted, or material came up to the surface and sublimated and left behind material along those cracks, those spreading air regions, perhaps. I mean, again, we had images of the surface. We just flew by with Galileo a handful of times for Europa, and not always very close. The images look amazing, but we didn't always fly all that close to the surface, right? Then there was when things got messy. We had, what do you call messy things? Chaotic. We have the chaos terrain, where suddenly those nice line after line of fractures is all broken up and chunked up, almost as if bits and pieces had melted, flipped over, and refroze with some matrix in between them, where you almost could envision putting them back together, but not quite. Again, telling us something about the dynamic history of this surface, of this icy world. And then there was the lack of craters. I mean, every other moon in the solar system that we had looked at, mostly up to this point, with caveat for special places in my heart like Triton, there weren't almost no major impact craters except for this one, which is a big one. And it doesn't have a lot of relief to it. And it doesn't look like a lot of impact craters, say, that we see on Mars, right? Because it's a different material with a different elastic response to those impactors. And then we see some harder to visualize but still present impact structures like this, where it looks almost like, perhaps if you've ever been ice skating in a cold climate, the beginning of the season when you're not sure if the ice is ready or not, what do? Okay, like normal people would like take an auger and drill, or obnoxious kids like me would take a brick and throw it off of the roadway and see if it broke through the ice or not. And if it punched through and left something like this, you didn't want to go ice skating yet. Not ready yet, right? Because it would leave these concentric punch-through structures in the ice. And then lastly, these lenticulae, these little, again, it's stretched color, but what you're seeing here kind of looks like something melted and came up to the surface. Right, almost like what you might see if you, say, had a subduction zone and had melt coming up to the surface, except this is all ice and none of that makes any sense. Can you subduct ice? Well, there are some papers now that say that you probably can if they reconstruct some of the tectonic history at the surface of Europa. But these were all visual clues that we got from looking at the surface of Europa up close with Galileo mission. We made other measurements, though, too, that told us about the interior composition and maybe the differentiation based on density and some gravitational measurements, right? So we had this rough idea, and this is a bit of a misnomer. We had this idea that it's got a metallic core and rock and then some level of water layer on the outside. You can't tell from density and gravity measurements that were made by Galileo that there was liquid water there, because liquid water and ice don't have a lot of mass difference between them, right? We had other evidence for this, which I'm going to get to in a minute. But we knew that there was a hydrosphere, that there was this region of ice, maybe molten, beneath that melted ice or ocean, beneath that, and then rock and a metallic core. And if we looked at the density and the gravity measurements, you could actually back out and realize that actually the amount of water at Europa is probably more than what we have across the entire surface of the Earth, even though it's a small moon. So thinking about the hydrosphere, thinking about the amount of water in a place, even if we didn't know necessarily if it was currently liquid or not, this is an exciting prospect to think about. Why did we think it was a subsurface ocean? Well, for one thing, even though Europa is obviously well too far away from the sun to be heated by by the solar radiance and melted, and it doesn't really have much of an appreciable atmosphere to hold that down, there is a heat source, an energy source, and that energy source is tidal heating. Because the solar system has gifted us a beautiful system with the Jovian moons, right? If a moon was orbiting in a non-circular orbit around a massive planet like Jupiter, over time, tidal heat would dissipate and it would circularize the orbit. So it would dissipate heat inside the body, but it would be of a short time scale and eventually circularize, and then you wouldn't have any more tidal heating because you'd be in a circular orbit. But Europa has friends. It has Io and Ganymede and Callisto in these resonant orbits. So every time Jupiter's tidal forces are trying to circularize that orbit, Ganymede will swing around and pull it back out, or Callisto will swing around and pull it back out. And those resonances between those orbits basically enable this tidal heating pump to continue for long periods of time because of the resonances between Io, Europa, Ganymede, and Callisto. So you have a long-lived tidal heat pump that's creating the heat that might be responsible for keeping this liquid ocean alive. And then I'll just play the other one because it didn't start automatically. Stretchy, squishy tidal forces interacting on the interior of Europa. But this is all stuff that I don't do. Fractures, impact craters, geology is not my sweet spot. What I love about this system, as Jody would appreciate from the next image, is Jupiter's magnetosphere, because it's big and it's beautiful. And again, gosh, nature just set up this great natural laboratory for us, because as you can tell from this nice animation that my good collaborator and colleague put together, Jupiter's magnetic field is tilted 10 degrees off of its rotation axis, which means that the magnetic equator oscillates over the orbital plane of the icy moons every time it rotates around, and Jupiter rotates like every 10 hours. So every 10 hours, the magnetic equator, as shown in this little video, oscillates up and down over the moons. I'm not going to do the full interpretive dance, Jody, that I did during my defense, but you get the idea. Magnetic equator oscillating up and down is driving a bit of a magnetic wave that's passing over these moons every Jupiter rotation. And just to highlight, it's a little hard to see still, but it's almost there. There's a little pink disk of plasma in the middle, known as the magnetodisk, to kind of draw your eye to where that magnetic equator is, because that's where the majority of the plasma is too. Since Jupiter's rotating rather quickly, Io is spewing out a ton or so of material every second and basically inflating this magnetosphere full of ionized sulfur and oxygen from Io's volcanism. And that plasma is then running into Europa and Ganymede and Callisto. So this is fun. This is Jupiter's magnetosphere, but it provides us a tool. It actually, when I say that we knew Europa had a subsurface ocean, it's because of the magnetic field. And that's a weird one to get your head around unless you realize that when we flew by Europa, we measured a magnetic field. But it wasn't an intrinsic magnetic field like Ganymede. It was a variable magnetic field that danced around depending on what Jupiter's upstream magnetic wave was doing. When it was tipped this way, Europa's field was pointing one way. Tipped the other, the other. This is a bad interpretive dance. I've got graphics to help with it. But if we think about it in terms of magnetic waves, which is what I like to think about, there are basically several periodicities that we are provided by the geometry of the system to use to magnetically sound the interior of an icy moon. And those are driven by, again, the tilt of Jupiter's magnetic field relative to the rotation axis, causing the magnetic equator or the plasma sheet to flop or oscillate over the moons. And then we also have the eccentricity of their orbits, because when they're at their apogee, I almost said apogee, but when they're at their apogee, right, then they're further away from the center of Jupiter's dipole field. And when they're at their perigee, they're at the closest point to Jupiter and therefore at the strongest part of Jupiter's magnetic field. So you've got this magnetic wave, and then you've got the closer, further magnetic wave, and they happen to be orthogonal to one another. So you can actually not just have two different wave periodicities, but they're on two different planes, which is kind of, again, Mother Nature setting us up this incredible laboratory experiment to magnetically sound the interior of icy moons. So we have these wave periods about 11.23 hours, which is, again, that Jovian rotation plus the orbital motion of Europa. And then we have 85.22 hours, which is the orbital period of Europa, giving you that eccentricity wave. And there's other harmonics of those waves as well, and BR, B phi, and B theta that is experienced at Europa, but we'll just focus on those two because the rest are just more of the same. So induction, the phenomenon of magnetic induction, I know you guys know this because you've taken E&M at some point in your life, even if you blocked it from your memory, okay? But this is based on Faraday's law, right? Faraday's law of magnetic induction, which is that if you have a changing magnetic field with respect to time, or as I've been describing it, a magnetic wave, right? That is going to create an electric field that drives currents within a conductive material. And those currents induce a magnetic moment that is synchronized and opposing the magnetic driving wave that is creating the currents in the first place. Yeah, does that sound roughly familiar? Kind of like if you take a copper pipe and drop a magnet through it, the eddy currents drive a current, the current drives an opposite magnetic field, and the magnet takes longer than gravity would tell you it should to fall through that copper pipe because there is a magnetic field pushing back against gravity, pulling it down. And it's driven by the fact that you've dropped a magnet, which is a changing magnetic field through this cylindrical conductor. And if your instructor didn't show you that demo, it's a really cool one, but they wouldn't let me carry a copper pipe on the plane. Instead, we'll do the diagram, which again, my colleague Corey put this together in PowerPoint animation style. Bar magnet, coil of wire, goes in, drives a current. Current drives an induced magnetic field that's opposite the magnetic field that's pushing the currents through in the first, developing the eddy currents in the first place. So take that picture of magnetic wave, which is just this magnetic going in and out of a coil of wire, and now it's Europa, and it's a magnetic wave being driven by Jupiter's magnetosphere. That's what we're measuring when we fly by. What that looks like in real time is Jupiter's magnetic field. Oh, this one is really hard to see. I don't know how to make it darker in here without just putting you guys fully in the dark. But can you see it all right enough? A little dancing dipole around Europa that's oscillating based on how Jupiter's magnetic field is oscillating over it. I don't know how to make it darker. So that's what we measured with Galileo. That's how we discovered the subsurface ocean, and that's how we're going to go back now with a dedicated mission to characterize it. And the way we do that is with just a bit more math, right? This is what we observe. The B here is the total magnetic field that we observe with the spacecraft, and that's based on the primary field, the driving field from Jupiter, and the secondary field, which is that induced field from Faraday's law of induction. So here's the secondary field. There's the magnetic moment based on the primary driving field. And if you don't worry about all the details of radial distance and the likes, just realize that, again, from this induction interaction, you have an amplitude A and a phase lag phi of how good a conductor it is that you're driving this magnetic wave through and driving these currents through. So we can actually use this to help us constrain and characterize the subsurface ocean in terms of the thickness of the ice shell, the integrated conductivity of the ocean, and the ocean's thickness. 3 parameters from the magnetic induction response. And it looks beautiful when things line up right. So if you imagine that the red is the eccentricity magnetic wave, and the blue is the oscillating magnetic field magnetic wave, if we can measure the amplitudes, the relative amplitudes of those responses, and they overlap, that will tell us uniquely the ocean thickness and the conductivity. This is like a best case scenario one because they overlap really cleanly. If you have a really precise magnetometer, you can tease this out. And you can do similar tricks with the phase and the conductivity and the ice shell thickness as well with the phase lag of the magnetic wave induced signal. this would be great. This is awesome. Physics at its best, except for one thing. We forgot about the plasma physics. This is just like super nice changing magnetic fields and conductors. And we forgot about the fact that Jupiter's magnetosphere is full of plasma from Io. And Europa, though diffuse, has its own ionosphere, which is also a plasma. And you can't forget about them. So, like I said, you can't discount the plasma. So this is a model that Camilla Harris, not Kamala Harris, a graduate student at University of Michigan, did just looking at what is the amount of magnetic field due to the plasma effect. So I've modified this equation. This is the total B, which is impossible to see now, the primary driving field from Jupiter, the secondary field from induction, but there's also a plasma contribution to the observed magnetic field that we have to suss out. We have to be able to subtract out if we want to truly isolate the induced response and be able to do that little nice map on the previous slide, right? And it turns out that the plasma contribution is pretty big, right? And so this just highlights with those same colors, if we get rid of the primary field, because that's easy enough to subtract out, we can model Jupiter's oscillating dipole wave field, right, and subtract that out. If we're just trying to look at the plasma contribution and the induced field contribution, they can be pretty comparable in size. And if you add them to look at the total field, it can really shift. If you only look at the total field, it can shift the amplitude and shift the phase, so you might get the wrong answer trying to figure out the ocean characteristics. So it's really imperative that we can either model out or observe and then model what the plasma contribution is to isolate the induction field to be able to characterize the subsurface ocean. And that's where people like me come in, right? That's, yay, cue the plasma dynamic modelers. Suddenly we're all employed with a mission, which is a rare thing. Modelers are never employed on missions, but we are on this one, and that's kind of a beautiful thing. So again, this is like, I was told not to just give a high-level Europa talk, but do a little bit deeper into the type of research contribution that I'm working on with it. This is where that's at, trying to understand the full plasma dynamic interaction at Europa so that we can isolate the induced response and characterize the subsurface ocean. And as someone who does love geophysics, I'm also interested in the ice sheet dynamics and how the ocean couples to the ice sheet, right? And which ways thermal energy is propagated, because we have indications from chaos terrain that maybe there was melt near the surface that reconfigured some of these ice fractures and icy shell material. And we have indications from plume observations from Hubble Space Telescope that there might even be some active geysering activity at Enceladus that is coupling some melt layer, maybe not all the way down to the ocean, maybe a subsurface, within the ice sheet melt lens or something like that, that is also enabling us to study what's going on, what's the plumbing in the ice sheet, what's the geophysics in the ice sheet, right? Not just how thick it is, which is also an important question. Okay, any questions? I feel like I'm going both slow and fast at the same time. Geysers, plume activity. We observe them with Hubble Space Telescope in the ultraviolet and a couple of other different ways as well that I won't get into. But they're exciting. They give us some sense that this isn't just stuff happened here and we see it in the tectonic record threaded across the surface, but that there might still be enough thermal transport, energy transport through the ice sheet that we're seeing dynamics active at the surface today. And why this is interesting and important is because it also gives us a mechanism for exchanging material from the surface down into the ocean and vice versa. So if stuff is coming up, precipitating on the surface, we can know something about the ocean composition, right? Because the water might sublimate away, but the traces of whatever salts, which cause the salinity, which cause the conductivity of the ocean, might be present at the surface. And it also takes some of the radiogenic material at the surface of Europa that's deposited from this incredible radiation environment that is Jupiter's magnetosphere, and move some of that material down through the ice shell as well. So really interesting things going on if there's really a flux of material between the subsurface and the surface. And if there's questions, I can see you're thinking away. You go ahead, because I might get this stuff wrong. And of course, what helped motivate a lot of the Europa Clipper mission was the astrobiology component. This is not a search for life mission, and I want to be really clear about that. Unless dolphins come diving out of the cracks and doing backflips in front of the spacecraft, even then we're not going to see them probably. This is not a search for life mission, it's a habitability mission. It's trying to understand the boundary conditions for life in the subsurface ocean and if it could be a habitable environment. And some of the ingredients which you all probably in this room are more familiar with than I am in terms of the astrobiology program here, which I heard is celebrating its 25th anniversary, which I should remember because it was getting kicked off right when I got here. You need water. And again, we already said that Europa has more water probably than the entirety of the Earth. Essential elements from formation and impacts. Chemical energy. Again, here we definitely have tidal heating, which is providing energy from below, but possibly even chemical energy from above as well if we have transport of material from the surface through the ice sheet as well. And stability, and this is one that I think is a fantastic one to consider. There are many habitable environments around the solar system. There's habitable environments, pockets on Mars that are probably habitable, but they lack stability. They lack longevity, perhaps, for life to evolve over the periods of time that we believe and understand life takes to evolve. You can't have like a pocket of subterranean water seepage that disappears seasonally and say, oh yeah, that'll maybe create an environment where life can evolve right at the surface of Mars, right? But here you might have this kind of simmering, long-lived subsurface ocean with all these right ingredients that might possibly be stable enough. We don't know. This is why it's a habitability mission, not a looking for life mission. We're trying to characterize and understand the ingredients that are present in the subsurface ocean. And of course, for those who like Earth, which we are in an Earth and Space Science department, this again, our mental picture of life on Earth really changed in my mind, and again, my course understanding as barely an astrobiologist, from kind of the warm, shallow pond method of thinking, like, oh, life had to evolve in these warm, shallow ponds near the surface of the Earth, or at the surface of the Earth, to, oh my gosh, the ocean floor is teeming with life far away from where photosynthesis and light is getting to because of the chemical energy provided at these hydrothermal vents. It doesn't need sunlight to make it happen. It doesn't have to be a warm, shallow pond. And I think this is really where people's brains start ticking and clicking the analogies to Europa, where you could have a long-lived subsurface ocean environment in contact with the mantle that might have similar ingredients to what we see at hydrothermal vents. So anyway, Europa mission in a nutshell is we're looking at ice shell, kind of geophysics of the ice shell and transport through the ice shell and ocean. We're looking at composition at the surface because that gives us clues to composition in the interior. We're looking at geology and geophysics, what's going on at the surface of the ice shell. Possible activity, are there plumes, are they active, will we be able to see them even if we fly right by them? Not just dolphins, but plumes of material. And reconnaissance, this was a big component early on, just thinking about the fact that if we ever wanted to land on Europa, we'd have to decide where, and we'd have to decide where was safe. Because even with all those great images from Galileo, we did not have the topography information probably to safely land anything, let alone know where was the most intriguing place to land. And for those of you familiar or not familiar with missions and how we scaffold them from our fundamental questions, this is the pictograph version of the questions. But what we usually start with is a science traceability matrix. Right? I can see those who know what this is and poured hours and hours of hair ripping and hair graying into this process. We start with our science requirements. What are the major questions we want to ask? And again, they're binned into ice and ocean, composition, geology, and current activity. The reconnaissance maps across all of these, obviously, because we want to know where to go, and these are going to be the things that dictate to us where we want to go. But these questions are the definitive what we want to answer with the mission, and they can't be pie-in-the-sky questions that don't have answers. We have to really refine the questions to something that we can achieve. Otherwise, how do you know if your mission is a success, right? You can't have a mission if you don't have some metric for what you want to get from it. So these questions took a painful amount of time to evolve the exact language and the requirements it gets us to the next. There are many more columns to this. This usually folds out into some massive long table. What are the requirements to address these science requirements, these science questions, right? What do we need to observe to get these answers, right? And then what tour requirements do we have? Like, where do we want to fly to see these things? How do we want to make the mission work from a kind of infrastructure point of view, and what the mission is going to look like? And then what instruments and what instrument capabilities do we need? And that's where really, for someone like me on the instrument side, we got a rough straw man idea of what the mission was supposed to look like from headquarters, because they said our next flagship mission is a mission to Europa. We think you'll need these instruments. Community, propose your instruments, right? And that's where the community finally got, rubber meets the road, and got to put in their best ideas, gather their teams together and say, we think we need a magnetometer with this capability. We think we need a plasma instrument with this capability. We want cameras, all the spectrums in the world, because we want to map the surface 9 ways till Tuesday to understand it. And that's where, from that, was born the Europa Clipper science team, because the instruments were selected. The co-investigators on those instruments make up the science team, plus or minus. There's additional people too, but that's the main backbone of the science team for the mission. And what that ended up looking like after the mission instrument selections were a suite of remote sensing instruments and a suite of in situ instruments. And I'll go over these in a bit more detail, but not a ton more detail. The ultraviolet imager, right? Then we've got our narrow angle and wide angle camera, our NAC and our WAC, which is a great acronym. MISE, our infrared spectrometer. ETHEMIS, our thermal imager and mapper. And REASON, our ice penetrating radar. These are all remote sensing instruments. And then below them, again in situ, we've got MASSPECT, which is our mass spectrometer. SUDA, our dust analyzer. ECM is our magnetometer, which I love. PIMS, I also love even more because this is one of my instruments, is the plasma instrument. The acronym for this is fantastic. There are a lot of Brits on our team, and they're like, PIMS, this is great. It must be the British influence, but it wasn't. It was Barry Mock who said, I'm tired of all these forced and tortured acronyms. Just call the darn instrument what it is. Plasma instrument for magnetic sounding. And the Brits went, perfect. They're Faraday cups and PIMS cups. And, it's a science team with a drinking problem. No, it's a drinking team with a science problem. Something like that. They're Faraday cups, though. No joking. Joking aside, they're Faraday cups. There's two sets of them. And then we have gravity and radio science, which is kind of an oblique component which uses the way we transmit the data back to also do science around the body from the Doppler shift and the transmission of the data. So this is what the in situ instruments look like. Just various pictures of them in progress. ECM, you can't really see the ECM, but this is the boom that it's out on, that extended out after launch. Many, many meters long with 3 magnetometers spaced across it. And then here's our Faraday cups, our PIMS cups. The remote sensing instruments, I like to think about it, everyone knows this picture, right? Or album cover, whatever you decide. That visible light breaks into the spectrum. But of course, we know that the electromagnetic spectrum is much more than just visible light, right? We cover the entire spectrum. This is the entire electromagnetic spectrum, and visible light is just a small part of it. And of course, with the instruments we have, we're covering that, right? The ultraviolet, ICE is the visible, infrared, and then REASON is radio waves, the ice penetrating radar. And if you hadn't seen them laid out on the spacecraft, this is what it all looks like. The magnetometer boom, high gain antenna, ginormous solar panels, because this is a solar-powered spacecraft. We don't have RTGs or MMRTGs on this spacecraft, no nuclear power. All solar panels all the time. Most of the instruments are strapped onto the spacecraft bus here, or bolted, not really strapped. But of course, the ice-penetrating radars, those guys deployed off of the solar panel. So first the solar panels folded out, and then, like the Sith Lord's double-sided lightsaber, those antennas expanded out off of the solar panels after the solar panels deployed. But we're not orbiting Europa. Clipper came to be because orbiting Europa was way too expensive and way too risky because of the high radiation environment. So Clipper, in fact, orbits Jupiter, and it flies by Europa about 50 times over 3.5 years, right? And this way, the closest it gets to Jupiter is when it flies by Europa. That's the closest into the radiation environment, and it's only there for a brief amount of time. It spends the other 2 to 3 weeks of its orbit further out away from the radiation environment, so we're only getting a limited dose of radiation instead of trying to orbit Europa and be bathed in that radiation all the time. And ended up being much better for the spacecraft, much less risky, and able to launch actually more science payload because you needed less shielding. And to visualize that, there's this neat little graphic, which hopefully works. It's so hard to see these. Shoot. You've got Clipper orbiting. There's Clipper. You can just kind of follow the name. And when it goes close into Jupiter, the rads jump up. But if it was orbiting at Europa, the rads would have been high all the time. So instead of getting an entire mission's worth of integrated dose, you get it in small bits and pieces. And they do add up over time, but it's at a much lower rate than we would have gotten if we were just trying to orbit Europa. So we build up all these orbits around Jupiter where we get an instantaneous high dose of radiation when we're close to Europa, but the net radiation taken on by the spacecraft is much lower, and it's a much safer, lower risk mission because of this infrastructure. And we get to cruise around the Jupiter system, but not do Jupiter system science, because we're only supposed to study Europa. But that's not true. We're going to study the system. We just can't tell anybody until we write the papers. Okay. Just some of the stuff about the mission in brief, because stats are kind of fun. How big the spacecraft is and architecture, like I said, there's about, does that say 50 Europa flybys? Yeah. Sorry, I had a bit of blurry vision there for a second because I can't wear my glasses and look up and look down. About 50 Europa flybys are going to occur over that 3.5-year time period. It launched in October of 2024, just this year. And it's going to arrive at Jupiter around 2030, then get to its first Europa flyby, 2031, and then we'll have a bunch of years of these orbits, like I said, maybe 49, maybe 52, maybe 53, depending on how things are going with fuel, until the end of mission. Again, 5 remote sensing instruments, 4 in situ measurements, plus the gravity and radio science, which is just our mechanism for telemetering the data and doing also cool science with that telemetrization. And we've got a radiation monitor on the system too, just to make sure that we really are getting the radiation dose that we thought we should be getting. For scale, about 100 feet. And just, if you haven't seen a Falcon heavy expendable launch, it's a big rocket. It's not as big as SLS, but it's a big rocket. Falcon heavy expendable is the biggest one after SLS that we have at the moment. And by expendable, that just means that these reusable rocket boosters that we're so fond of watching land, right, when they come back down and land on platforms and you're like, yay, we're reusing rockets. We didn't reuse the ones from Clipper. We used every last bit of fuel on them to get Clipper out and about. But we did recycle them from Psyche's launch. So when you see the real rocket in a few moments, you'll see that they look kind of dirty and beat up. And that's because they were the recovered rocket boosters from the Psyche launch a year and a half earlier. Then we've got Clipper, which is all folded up and shrunken down inside the fairing. And Clipper's roughly the length of a basketball court. And we're not at Oregon, so I didn't put the Oregon basketball court because, UW, Oregon, it's a thing. What did the instruments look like when they were getting built and put together? I mean, it looked kind of gnarly and awesome going down to JPL and seeing it being assembled in the high bay. All the instruments were coming in, like every few months another instrument would arrive and they'd start putting it on the spacecraft bus and put the high gain antenna on the spacecraft bus and then take it off and then open the electronics bolt and then close it again, hang it from the ceiling by cables. It was a pretty remarkable assembly process that took several years. That's the high gain antenna there. That's that spiraling arm for the mag boom. There were several deployment tests where the mag boom would expand out and then come back in. There's the solar panels. They never went to JPL. They went straight to the Cape because they're huge. They're the size of school buses. So they just sent them right to the Cape because we weren't going to strap them on the spacecraft and then put them in a plane and ship them that way. lots of fun stuff going on in terms of the integration of the payload. There's, again, some more of the solar arrays down at the Cape hanging and deploying. You see that they're hanging on a scaffolding because they really weren't designed to be deployed in 1G. So they have to, when they test how they deploy them, they can't just try and stick them out there because 1G would probably snap them off. So they have to kind of hang them as they deploy them to balance out the G forces and see if they really will deploy properly, even though we're at the surface of the Earth. And then the last tests that were really done before shipping the main spacecraft body from JPL were the TVAC, or the thermal vacuum chamber tests. And this is where they shake and bake, basically. They put the whole spacecraft in this 13-story tall vacuum chamber with intense thermal heat lamps and bake it and make sure that nothing bad happens to it in that process. And it was crazy. I got to go in the building and see it inside of this like vaulted 13-story vacuum chamber, and it was just absolutely insane to see. But once it was all ready, they shrink-wrapped it, final testing, and then they packed it up. And you might know this guy, or you might not, depending on how much you like to watch wholehearted, good family fun TV. If you have a little kid, then this show is awesome. But they said goodbye to the spacecraft, the main bus of the spacecraft in May. It got to Cape Canaveral and got unpacked. Solar panels got stuck on, everybody is happy, and it got closed into the fairing, which is really the last time that human eyes were laying on the spacecraft because it would only open again in space. And then, for those who were tracking the news, we hunkered down for a giant hurricane, which was not a hurricane a few days before when I took off from Eugene Airport. It was a disorganized set of storms. Okay, then. It was a disorganized set of thunderstorms that weren't going to turn into a hurricane. And that was a lie. That was a terrible lie because it turned into a gigantic hurricane, Category 5 hurricane over the Gulf of Mexico. And so we put the spacecraft fairing happily away in the assembly building, and then the science team away inside the hotel shelter, which was a good idea because then a tornado also hit the hotel. After the Hurricane I passed directly over Cape Canaveral launch pad, basically the day of the launch that was supposed to happen. So we didn't launch on the 10th of October. We launched on the 14th after this went through, and everybody recovered on the Cocoa Beach side of Florida at least. And then we had some nice glamour shots. So it finally got to roll out to the pad. There was a comet out, so beautiful clear skies after storms. That's a thing that happens. Moon was out. Again, the beautiful glamour shots of the spacecraft out at the launch pad ready to go. Everyone biting their nails because most of us had flights home and we really wanted to be there for the launch after weathering the hurricane and the tornadoes with my child, my parents, my cousin, her fiance. Like, so much family came out to watch this and then sit through the hurricane and the tornado and power out. This is sunrise morning of the launch. And then the launch itself, which I did not take this video. My husband did because I was too busy watching and didn't even, I had my phone out and I thought I hit start and I didn't. I just was watching, and then thankfully he was smart enough to hit go on it. I have no idea what volume this is at. It might just be my computer. So it's launching, it's beautiful. If you're counting for the speed of sound, you know that it's around 3 kilometers away, and now the shock wave of the launch hits the stands, and it's not as impressive through the sound on my computer speaker, but it was enough you could feel it on your chest shake you, because it is a big, big rocket. And it was a beautiful, clear day, and you could see it go very far up before it finally went through some wispy clouds. Amazing. I have seen launches at the Cape, but never my thing launching, and it was extra special. I can only say that much about it. We won't watch it again, though. So Clipper's journey. This is the Clipper tour as it's making its way, or cruise as it's making its way out to Jupiter. So we launched on 10/14. Then the next thing that happened was just not that long ago, right? On March 1st, we flew by Mars, tested some instruments out when we flew by Mars. It was a pretty nice thing. So there was the launch. We flew by Mars, yay, took some measurements. There may or may not be a science paper coming out of the PIMS and magnetometer. I'm not allowed to talk about that because we're not doing any science other than Europa science, but, you know, CMEs happen. They may or may not have been picked up by Earth, and then we measured them at Mars. I'm just saying it's going to be cool. Then we're going to come back and fly by Earth. This hasn't happened yet. This is actually, to the keen eye, is a real image of the JUICE spacecraft flying by Earth last year when it flew between the Earth and the Moon on its way out to go orbit Ganymede. And then we're going to arrive at Jupiter, right? That's this nice background image of of Europa Clipper at Europa, and Jupiter do its main cruise, and then the mission ends. We run out of fuel. We have to do something with the spacecraft. I mentioned that Galileo took a nosedive into Jupiter. We thought that would be too boring. So in a true full circle closure journey, we're going to smash Europa into Ganymede's face while JUICE is orbiting it and watch it crash. For me, it's a full circle moment because I started at Ganymede, and now Clipper is going to end at Ganymede. And that feels somewhat poetic, and I like it. But this is, you know, after 4 years of orbiting, 50 flybys of Europa, this is where it's going to end. And there were a shoot-ton number of people that were involved in this. This is just some of them at JPL, and some people who submitted their photos from all over the country who weren't there for the big group photo, because that's how things work. Hundreds and hundreds and hundreds of thousands of engineers have touched this spacecraft. Thousands of engineers, hundreds and hundreds of scientists over a 10-year journey. Our instruments were selected right around the time I had my son. So like I was working on the proposals. I was telling Jody I flew to work on a proposal at 7 months pregnant to submit an instrument proposal. We were selected right when my kiddo was born. He's 10. He went to the launch at 10. We're going to get there when he's like 16, and it's going to end when he's like going to college. These are long-scale missions to go to the outer solar system. It's not for the faint of heart. These are lifetime missions, or it's his lifetime mission. And it's kind of amazing. We had a lot of public engagement with this mission as well. The Message in a Bottle campaign. I don't know if any of you put your name on the spacecraft. I put my name on the spacecraft. I think my dog's name is on the spacecraft. Kid's name is on the spacecraft. It was a lie when they said you're going to Europa, because actually we all know it's going to go to Ganymede, but that's fine. It's going somewhere. But they were all etched on the spacecraft. There were, I forget how many, something like 3 million names on the spacecraft at the end of the day. And we had the U.S. Poet Laureate do an incredible poem that's also on the spacecraft, because we have this beautiful plate on the side of the spacecraft that has her poem in her handwriting. We've got Ron Greeley here, the Message in the Bottle campaign in general. And then on the back side of this plate is etched, this is a tantalum metal plate that's bolted on the side of the spacecraft. It's about 7 by 11 centimeters, so like, or inches, sorry, not centimeters. So like this big. And this is, all these are the sound waves for the word water in like 103 languages. And in the center is the symbol for water and American Sign Language. So kind of a tribute to water, a tribute to the mission, and very artistically done. So I don't know with the volume situation if you guys will hear this or not, but this was the Message in a Bottle poem read by Ada Limon.
In praise of mystery.
I don't know if you can hear that at all.
Poem for Europa.
Yeah?
Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the song
So there was a lot of thought that went into the mission, from the science traceability matrix and the instruments to how we communicate it to the general public. For graduate students, I encourage you to always think about how to communicate your science to the general public. To students, to inspire the next generation, I thought some of the work they did on Clipper was absolutely outstanding in that regard. And I'm happy to take some questions from you. Thanks for your patience.
Wow, thank you so much for that talk. I'd like to open up the floor specifically to any students who have questions.
Hello, thank you. Wonderful talk, by the way, but I was just wondering, because I saw one of the instruments was a ice-penetrating radar antenna, I believe. And I was wondering, does it mean we're going to get radar images of the underwater surface of Europa? Is that the intention?
That's a great question, and it's a complicated question. A lot of it depends on two things. One, how thick the ice shell is, because there's a limitation on how much power we can supply in the ice-penetrating radar and to be able to get the signals back. And two is the thermal profile of the ice shell. With warmer ice comes diminishing returns on the radar reflection, so the more of a thermal gradient there is, if there's too much thermal gradient before you get to the ice-ocean interface, you won't be able to see the ice-ocean interface the way you would, say, with Lake Vostok or something like that, where you can really see clearly where the reflections come back from and where they stop. So it was not the hope that the ice-penetrating radar would, its goal was not to detect the ocean interface. That's something we should get from induction, but it's a really incredible opportunity to use the ice-penetrating radar as a supplementary measurement to confirm the ice shell thickness if it does measure that interface, as well as doing the geophysics of the ice sheet, which its real intent is to do. What's the plumbing? What's the thermal transport? What's the structure of the ice sheet? Is its real science goal. But I hope that we see it. And I think roughly the numbers we've thrown around, I'm also on the ice-penetrating radar team as their resident plasma person, because to them plasma is noise, and to me it's the ionosphere. And so we take out the ionosphere for me, and then they can have the unpolluted signal to look at the ice. But the hope is that if the ice-ocean interface is within, say, 20 to 25 kilometers, we might be able to see it.
Okay, that's pretty cool. Thank you.
I was wondering, what are you expecting to find from your instrument?
So I think there's a lot that we hope to find. I mean, finding with a plasma instrument is a little bit different than finding with a camera or a remote sensing instrument, right? We might find evidence of an active plume with the plasma instrument. That's a very real possibility, because we would see an enhancement in the background plasma density over a specific region or something like that. With the plasma instrument, though, the biggest contribution that the plasma instrument makes is telling us what the upstream plasma environment is from the Jovian plasma disk, which again is made up of sulfur ions, oxygen ions, O2 plus ions, what that condition is when we fly by and measure the total magnetic field, because then we can use that to model out the plasma dynamic interaction and isolate the induction response. So oftentimes the plasma instrument and the magnetometer are viewed as kind of a joint science investigation, because the magnetometer will measure the total magnetic field and then try to parse out what's the induction response, what's the background response, what's the plasma response. And it's the addition of the plasma instrument that helps us really determine what the plasma dynamic contribution to that signal is. Does that help?
Thanks for this talk. This was really cool. I wonder if you could elaborate on the, you mentioned like subducting ice. How would you find evidence for that with this mission?
So this was a paper by Proctor and Caterhorn. I forget the year on it. Do you remember the year? I'm blanking at the moment. Yeah, okay. That's good because I thought it was 13 as well. But basically what they did is they took a giant map of Europa and all those fractures on the surface, and they looked at places where they didn't align, and they basically cut it up and figured out that if you backed it out, they would align, and so they used that as evidence for subduction. There's nothing in the relief that really supported it other than the lenticulae, the idea that if you had something subducting and melting, it might create these small chemically discrete pockets near the surface. But it was really a reconstruction of the fractures and sliding it around. And literally what I have seen in pictures was a giant printed map of Europa's surface and a lot of scissors and highlighters reconstructing where they felt those regions had disappeared from. Does that sound about right to you as well? I mean, it's still somewhat mind-boggling that it could happen, but so many things that we observe cause us to think more clearly about problems than with the blinders that we have from Earth when we're doing planetary science. So there may be other things that we're not as thoughtful about that could enable driving that subduction, maybe in the thermal convection and things like that within the ocean, other processes that might be contributing to it. But it is still boggles the mind. I fully agree that we could have subduction and not just fractures occurring from tidal forces.
When you were showing the ice layer, water layer, rock, and then metallic core, do you know, I guess you were saying you don't know how thick the ice is yet, but then, or how deep the water is then, but then would you also expect from the heat to also see like activity in the rock layers as well?
I mean, I think there's an ongoing debate right now about what is happening at the mantle ocean boundary, or if that really is an energetic exchange. There was a bit of a hot spot moment at AGU where Paul, what? Oh, Byrne, yes, sorry. My student's a Paul also, and I'm like, it's not that one. Paul Byrne stood up and said, Europa's dead. There's no way you can have fractures or any sort of dynamics getting, if you take away the ice and think about the mantle as a crust, it's not going to happen. And I think there's a sound reason that paper hasn't been published yet, and that's because it's very, it got a lot of attention, but it's not maybe all the way thought out in terms of how it was presented. I'll say it gently, because I like Paul a lot, but I think it's not a well thought out paper. But it's true, we don't have a way to image it. We don't have a way to see it. And so the best we have to offer in terms of thinking about it is to better understand the conductivity in the ocean and to better understand the thermal profile at the surface, which is probably an expression of the exchange of thermal heat from the mantle through the ocean into the ice.
I actually have a question for you. I'd like to back out and kind of look at something that you just spoke to and the human element of this. Something that I am constantly struck by when looking at NASA missions like this is just how much collaboration and like cross experience across all types of walks of life, like how people come together to make a mission like this work. And so for those of us who are early in our careers and just looking into maybe working on something collaborative, maybe not to this scale, but for those of us who are looking to make those connections and make those, I guess, scientific jumps into different silos, what advice would you give us?
Be open-minded and willing to take risks. If you see an opportunity to collaborate with someone, if you run into someone at a meeting who's really excited about your work and sees maybe a mechanism, don't be afraid of taking the chance and the opportunity. It might be a red herring. It may not pan out as a published paper, but it will widen your network. It'll widen your ability to talk across disciplines and enable you to be seen as someone who can talk across disciplines. So I think the best way not to feel pigeonholed or siloed in such an interdisciplinary community where so much of the mission work is really, like you said, this web of diverse perspectives. I mean, and and we can say diversity in this room, even if we can't say it at NASA. But this web of diverse perspectives from disciplines, from experiences, from comparative planetology, from earth sciences mapping out to the planets. The best way to not be siloed is to not let yourself be siloed, but to go to those talks in different disciplines, to see the connections, and to be willing to take a chance when someone reaches out to collaborate on something and you're not sure. I think one thing I've been bad about is saying no. I'm always like, yeah, let's do it. And then sometimes it totally doesn't pan out, and you're like, wow, that was a lot of time, and I now have a really good colleague and friend, but it totally didn't work as a paper, or didn't work as a project, or didn't get funded, even though we put in the best proposal ever, obviously. And then you can put that project on the side and maybe come back to it at another time. But I'd say don't be afraid to take some risks, and definitely take the opportunities when they arise. And it might come along in a myriad of ways. It might be a summer internship. It might be an opportunity to postdoc with someone who is a little bit different than you. I think the scariest jump I made was moving from here, working as a modeler in a modeling group, to going to SWRI, where they didn't even know how to get me a Linux machine because they were only doing data analysis. There were no modelers there in San Antonio, and I had to build my own Linux machine and put all my own compilers on it and build them from, because no one even knew how to do those things. But it put me in a building full of people who work on spacecraft, who work on instruments, who do data analysis, and that was something I didn't do as much of for my project. I pulled published data to compare to the model. I developed ways to compare the model to real data, but I hadn't actually worked and thought about the sensitivities and the observations, the uncertainties and the observations, error. What's error? It's the answer, right? There's no error when you make a measurement, right? There's no error in my model, that's for sure. But I mean, it was a leap of faith because I didn't speak the same language. And that was a risk on their part and a risk on mine, but I learned a lot from it, and I think it positioned me to be able to talk to the instrumentation side and to be invited to join as a value-added proposition to PIMS and to Reason, where they hadn't previously thought about adding modelers before, but because I knew how to talk to the instrument teams, I knew how to talk to the data folks, I knew how to tell them, this is how I would compare what you measure to the physical framework, that made it appear value-added. And it wasn't just me, Shinja Jha, there were several other modelers who in the past would never have been invited onto instrument teams at that early stage, who were brought on board because it was seen as valuable. So be bold.
Hello. I was wondering if you could elaborate a little more on how the... Oh, sorry. I was wondering if you could elaborate a little more on how the composition, and you mentioned the conductivity of the ice and subsurface ocean impact the induced magnetic field that we're going to measure.
Sure. And I put up the simplest diagram. We call them, I call them, many call them the confusograms. If you want to see a genuine confusogram, go to the Zimmer paper in 2000, where they first do this induction phase lag amplitude relationship to conductivity, ice shell thickness, and ocean thickness. And it's messy. And it is confusing. And it has taken me hours of staring at those to really understand, okay, where are the unique solutions and where in the parameter space are the non-unique solutions, which is why we need other instruments to help confirm. The way I like to think about this is that, composition, right? We're going to get conductivity, and that will tell us something about the salinity, and maybe different conductivities based on what kind of salts might be in the ocean, right? And there are papers on this. Not my area of expertise, but other people's areas of expertise. But the way I like to think about, again, the diversity of perspectives that are brought by different instruments is if you have 5 different instruments looking at Europa, trying to understand whether or not there's a subsurface ocean and what its characteristics are, and you have uncertainty or non-uniqueness in how you interpret the conductivity and hence the salinity and composition from induction, well, now you have the composition measurements at the surface. And they're going to have different uncertainties and non-uniquenesses, and is the surface directly connected to the ocean? And then you're going to have another ice-penetrating radar that might help you constrain the ice shell thickness, based on, as to your question, right? And if that helps constrain one of those three parameters, you start to shrink the uncertainty. And the more lines of evidence, the more different perspectives you get that have their own sets of very different uncertainties, if you're still converging on the same answers, then you know you're probably on the right track and going down the right path. There are some solution spaces which are more unique and more confident, and those are the ones you hope you land in. But sometimes nature isn't clean like that, and that's why we have this array of instruments trying to get at these questions and not just a single instrument package. I don't know if that helps or hurts, but in terms of the conductivity, it is complicated because conductivity is a value, and that value tells you something about what salts are dissolved in the water, right? But it's not a unique solution in terms of what, how much, I don't know the salts. Sodium chloride versus magnesium, different things, chemistry, that was one I didn't do, right? All those different components, it's a little hard to say just wrapped up in Siemens per meter, right? And just in conductivity. But if you have other lines of evidence that help say, like, gosh, we see all of this magnesium, sulfur stuff on the surface, it's probably not sodium, right? Then you can help collapse it down a bit more and feel more certain about what the composition is. The induction experiment is not a super good measure of composition. That's why we have many other instruments to help us with that. Yes. Yeah. I would say from my non-expert side as a solar system evolution person, because I am not an expert in that, but I would believe that because of the location that the moon's formed being well beyond the ice line, that these are things that accreted in process, right? And there's other forms of heat, there's radioactive decay, there's thermal heat from coming together, but those timescales are much, if it really was that it all came together, that wouldn't be enough heat to keep an ocean liquid. The tidal heating and the fact that there are these resonant orbits with the other moons kind of forcing it to stay in an elliptical orbit and therefore enabling this tidal heat pump to persist. I think that's really the persistence of the tidal heating source is what's keeping it liquid. Well, it's a good question. Ganymede, they think, has a subsurface ocean, but it's likely wedged between two different layers of ice and not in contact with the mantle. Callisto, it depends on which papers you read. Some of them say all of the induction signal is from Callisto's much thicker ionosphere, which it possesses and the other moons do not as much. And some say no, that can't explain all the times we flew by and saw an inductive response. It must be that there's a subsurface ocean, even though from the gravity measurements it appears to be not differentiated, which is, I don't know what that means. It always is kind of visualized as kind of cookies and cream ice cream, whatever that is. My kid wants to eat it, but I don't know what that means for a subsurface ocean. We don't have enough data from Callisto to really resolve that a priori. But we'll get a bunch of flybys of Callisto as we gravitationally pump down to be in this orbit where our Perijove is at Europa. We'll have some Callisto flybys, we'll have some Ganymede flybys, and the same goes for the JUICE mission as well. It will have a suite of Callisto flybys, Europa flybys before it goes into orbit around Ganymede.
All right, well, I want to be respectful to everybody's time because we are after time. And I just want to encourage everybody who still has questions to come talk or reach out to Carol. And let's thank her for her time.
Thank you, guys.
Just a reminder that we will be commencing again with the gala tomorrow morning at 10:15 for the Structural Petrology and Tectonics seminar. We will have the upgoers in the afternoon at 1 o'clock. And then if everybody could please join us for the award and reception, that will be in Kane Hall on the second floor in the Walker Ames room from 5:30 to 7:30. Thanks.